Hey everybody. So we're still talking about the other trig functions. So we've got 6 of them now: sine, cosine, tangent, cotangent, cosecant, and secant. And we went through the definitions in the previous video. We're going to look at this hopefully somewhat short one, some properties of our trig functions. And the first properties we're going to look at have to do with even and odd functions. So I want to begin with a little review of what even and odd functions are. So an even function if we have a function f and it's an even function, what that means is if you evaluate the opposite of an input, it's the same as evaluating the input, right? So if you change the sign of your input, it doesn't change the output. For example, let's look at f of x equals 3 minus x squared. Okay. Suppose I have some number a, then f of a would be 3 minus a squared. Well, let's look at f of negative a. This would be 3 minus negative a squared. We'll do a little algebra. I can rewrite negative a as negative 1 times a. That's all squared using the properties of exponents. This is negative 1 squared times a squared. Negative 1 squared is positive 1. 1 times a squared is just a squared. And we end up with 3 minus a squared, which was exactly f of a, right? So we've seen that putting in the opposite of a number is the same as putting in the number itself. That means we have an even function. This also has an interpretation graphically. If we look at the graph of this function, 3 minus x squared, this would be a parabola facing down with its vertex up at 0, 3. Right? And it would be symmetric over the y-axis, meaning if you reflect it over the y-axis, it is an even function. This is one of the ways we can tell when we have an even function besides this definition, right? For instance, this is the point root 3, 0. This is the point negative root 3, 0, right? So any point over here has a corresponding point over here where you have the opposite input, like the negative root 3 and root 3, but the same output, right? The opposite input, the same output. Okay, that's an even function. An odd function has a similar definition. If you take a function and put in the opposite input, you get the opposite output. Okay, so f of negative x is the same as negative f of x. And this is a good point to be clear that this does not split up all the functions. There are plenty of functions that are neither of these. These are just 2 of all the possible categories we can throw functions into. So not every function has to fit into one of these. And most functions don't. These are both fairly special properties and very useful when we have them. Let's do an example of this one. Let's look at the function f of x is equal to x minus 2x cubed. And let's see. So we'll have, yeah. So if we have a as a number, f of a is equal to a minus 2a cubed. Let's look at what happens to f of negative a. You get negative a minus 2 negative a cubed. We'll play a similar game. So I've got negative a minus 2, negative 1 times a cubed. Exponents, let me, the rules of exponents, let me split that exponent over, or distribute that exponent over both of those when they're multiplied. We get negative a, so negative 1 cubed. Oops, sorry, I don't need that parentheses. Negative 1 cubed leaves me a factor of negative 1 times a cubed. Let's factor a negative out of both of these terms. So I have negative, what's left is a. I've got this negative here I'm factoring out, so minus 2a cubed. But look at what this thing right here is. This is just f of a, but we've got a negative out front. So f of negative a is the opposite of f of a. Okay, so this is also a nice property that functions have. Let's look at the graph of this function. This is going to be a cubic function. Let's see, it has roots at 0. If we set x, set this equal to 0x, and x minus 2x, whoops, 1 minus 2x squared equal to 0. We get roots at 0. And plus or minus 1 over root 2. And so let's see, those are, I'll put them here and here. It's going to be going down in the, as we go off, oops, as we go off to negative infinity. So just a quick sketch, something like this. Okay. Now I haven't drawn it perfectly, but what is true, if I had drawn it perfectly, is if we rotate this, if we rotate the function, so for instance, let's just look at this side. If I rotate this around the graph, it will fit right on this. Sometimes people say it's symmetric about the origin. If I rotate that thing 180 degrees around the origin, you wouldn't be able to tell the difference. Okay, it's symmetric about the origin that way. Okay. These are really nice features of functions. When you know you have an even or an odd function, lots of things that we do become much easier. I've seen entire pages of calculations be able to be expressed in a single line when somebody simply notes this is an even function, so by symmetry or something like that. We won't do much of that now. We're laying the groundwork for stuff that will come in your calculus and later courses, but needless to say, these are, maybe it's not needless to say, these are important features of a function. So let's now take a look at these ideas in context with our trig functions. So let me draw our nice unit circle. Okay, so there's a unit circle. Let's look at, let's put in an angle. All right, so here's our angle theta. We know it goes through some point x, y. Notice, let's write cosine of theta equals x, sine of theta equals y. That's our definition. Let's now imagine the angle that's negative theta. So that's the same sort of amount of turn, but in the opposite direction. All right, so this is going to be negative theta. So what should happen here? You can use a few different ways to justify this to yourselves. Similar triangles is easy. We can see two triangles there that have the same, they're both right triangles with one angle the same, so the other angle's got to be the same. They've got the same hypotenuse, so all the sides have to be equal. And what that all boils down to is, well, there's 2 points on a vertical line. They're going to have the same x coordinate. And since the heights of these two similar triangles or congruent triangles are going to be the same, this distance is going to be the same for the y coordinate, but it's in the opposite direction. So if the coordinates up top are xy, the coordinates when we reflect down below are x negative y. So what does that mean? Well, cosine of negative theta, we look at the x coordinate, is exactly the same. Sine of negative theta, however, is the opposite. In other words, cosine of theta is the same thing as cosine of negative theta, while sine of negative theta is negative sine theta. This is the definition of being an even function. This is the definition of being an odd function. And this is so I've drawn it for an angle in the first quadrant. I encourage you to explore what would happen to angles in other quadrants, but it will always work out this way. And so cosine is an even function and sine is an odd function. And we can categorize all of the trig functions. So let me make a little list. I'll let you go through the geometry to do this. Our even functions are cosine and secant, while our odd functions are going to be sine, tangent, cotangent, and cosecant. All right, so 4 of them turn out to be odd, 2 of them turn out to be even, right? So let's be really careful about what this means. Cosine of negative theta is equal to cosine of theta. Secant of negative theta is equal to secant of theta. On the other side, we have that sine of negative theta equals negative sine theta. Tangent of negative theta is negative tangent of theta. Cotangent of negative theta is negative cotangent of theta. And cosecant of negative theta is negative cosecant of theta. Okay, so for example, if we know that, let's think of one we know here, cosine, let's do a secant. We know that secant of pi over 6, what's that going to be? 2 over root 3. Then we know that secant of negative pi over 6 is exactly the same thing. On the other hand, we might know that cotangent of pi over 4 is equal to 1, which means that cotangent of negative pi over 4 has got to be equal to negative 1. Right? This is because this is an even function. Here, we're using the fact that this is an odd function. Okay. When we get into graphing these functions, we'll also see similar features that I showed with these examples here, but we'll get to that in a little later section. Okay, let's add one more idea to this now that we have all of our trig functions. We learned previously the Pythagorean identity that sine squared theta plus cosine squared theta is equal to 1. Okay. Well, now we get some alternate forms of this with our other trig functions. So let's start with, they can all be found using this. Sine squared theta plus cosine squared theta equals 1. Let's divide both sides by cosine squared theta. Well, let's look at this sine squared over cosine squared. Sine squared theta over cosine squared theta. Remember what this means. This is sine theta squared. This is that notation that I consider an abusive notation, but it is prevalent. It is used everywhere. This is, let's go down, sine theta, cosine theta, or sine theta over cosine theta, sine theta over cosine of theta. But sine of theta over cosine theta is tangent of theta, which means we end up with tangent squared theta. So here we have tangent squared theta. Cosine squared over itself is 1. 1 over cosine squared theta, remember the definition of secant as being the reciprocal of cosine. And we get this nice identity. Okay. Let's do one more. Again, starting with that original identity, which remember comes from the formula for a circle, or equivalently, the Pythagorean theorem. This time we're going to divide everything by sine squared theta. Well, now we get 1 plus cotangent squared theta in the same way as what we worked out over there is equal to cosecant squared theta. Okay. So now we have 3 forms of the Pythagorean identity. Okay. A little word of warning. There is if you want to get a little preview of what's coming, you should take a look, Google for a review of Trig identities. This is the first of many, right? There are a multitude of reasons that trigonometry is a powerful tool. One of them is this list of identities. It gives us a lot of power algebraically. We can get ourselves into sticky situations and using trigonometry and these identities, manipulate things until something useful emerges. Okay, this is one of those things that's a little bit difficult. We'll try to find some good reasons to use it, but most of the best reasons come later. For instance, in calculus, these identities are profoundly helpful at times. And so right now we're a little bit just learning to use these tools before we precisely know what the use of the tools is. But anyways, this is the first of many identities. Let's do one example to finish up. Let's suppose we know secant of theta is equal to 5/3. And theta is in quadrant 4. Okay. Let's find the other 5 trig values. So we've got secant of theta is 5/3. Let's go with the easy one. We know that cosine of theta is 3/5, right? That one we get straight away because we can take the reciprocal. Let's use this identity we have right here. Tangent squared theta plus 1 is equal to secant squared theta. So that means tangent squared theta plus 1 is equal to 5/3 squared. Well, this means tangent squared theta is equal to 25/9 minus 1, but let's write it as 9/9. And when we take the square root, let's take the subtraction first. Tangent squared theta is equal to 16/9. So that tangent of theta is equal to plus or minus 4/3. Right? So recall how we decide which one it is. Quick sketch here. We're in quadrant 4 down here. Here's our unit circle. Since theta is in quadrant 4, it means our angle is somewhere down here like this. Right. Or possibly going around this way. It doesn't really matter. The values of the functions are the same because these would be coterminal angles. Or maybe it spins around 1,000 times before landing in quadrant 4. Well, a couple ways to think about this. Tangent is sine over cosine. Looking at this picture, sine, the y-coordinate is negative. Cosine, the x-coordinate is on the right side, it's positive. You have a negative over a positive, that's going to be negative. Or in the previous video, I mentioned that tangent gives us the slope of this terminal side of the angle. In this case, it's clear the slope is negative. So we know that the value we want here has to be the negative one. Okay. We can do a similar game to get sine squared theta because we already have cosine squared theta. So we get sine squared plus cosine squared. I'm now using this piece of the puzzle. Cosine squared is 3/5 squared, or 9/25 equals 1. If I subtract 9/25 from both sides, I get 16/25, and I take the square root and I get 4/5 plus or minus. But the same thing we just did lets me know that it must be not minus because I'm in quadrant 4 where all the sign values are negative. Let's see, what else do we have to do? Cotangent is simple. We could, sorry, no, we can't yet. Let's just get cotangent from the tangent. They are reciprocal to each other. We can look at the definitions to see this, or we could take cosine over sine. That's another way to get this. And then cosecant theta, we could use this identity. An easier way is to note that it's the reciprocal of sine, and we get -5/4. Okay. All right, those are the other trig functions, our new Pythagorean identities, and all right, even and odd functions. Okay, that is it for this one. Thanks, everybody. I will see you next time.